by finishing the information we were going over on Tuesday. Which we were going over intermolecular forces and how they play on the physical properties of a substance. What we were up to is this concept of vaporization. And I'm going to pick up with a couple of slides that we actually went through just to get our minds back in gear on vaporization and vapor pressure. So no matter what temperature, 10 degrees Celsius, 100 degrees Celsius, doesn't matter. At all temperatures, liquid substances will, some of those molecules will go into the gas phase. So it doesn't matter what temperature, you're going to have vaporization, meaning some of those molecules, especially surface molecules, are going to gain enough energy in order to escape the liquid phase and go into the gas phase. Now, if you have an open container, all you're going to have is vaporization because the vapor is going to escape into the atmosphere. But if you have a closed container, then you can determine the vapor pressure. You can determine how much vaporization is occurring at that particular temperature. So what happens when you have a closed container? You have your gas molecules that are gaining enough energy in order to go into the gas phase. These gas molecules, just like all gases, are moving in every possible direction at fast speeds. When they collide with a surface, they apply pressure at that location. That is vapor pressure. Now, these gas molecules are going to move around, but at some point they are going to lose some energy. So some of those gas molecules will wind up back in the liquid phase. At the point where the liquid molecules are going into the gas phase and the gas molecules are returning to the liquid phase, you reach a state of dynamic equilibrium where the number of gas molecules does not change. Now, with respect to our intermolecular forces, how does intermolecular forces play on vaporization or vapor pressure? Well, the stronger these forces are in between these molecules, the harder it's going to be for those molecules to gain sufficient energy in order to escape into the vapor phase. So the stronger the intermolecular forces, the less vapor you have. The less vapor you have, the less vapor pressure you're going to have in a closed container. So when we were talking about intermolecular forces and boiling point, we said increase intermolecular force, increase boiling point. Increase intermolecular force, increase melting point. Increase intermolecular force, increase viscosity. Increase intermolecular force, increase surface tension. In other words, all of the physical properties that we have discussed to this point, if you increase one, you increase the other. Vapor pressure is the opposite. If you increase the intermolecular force, you decrease the vapor pressure. Again, we decrease vapor pressure because if you increase the intermolecular force, those molecules are going to require more energy before they can escape into the gas phase. Therefore, at any given temperature, if you have strong intermolecular forces, you're going to have fewer molecules that are in the gas phase. And fewer molecules in the gas phase means a lower vapor pressure. So all this does is it explains that the stronger the intermolecular forces, the less vaporization that will occur. And the less vaporization that occurs in a closed container, the lower the vapor pressure. So that's just putting in writing what I've already stated. Now, with this whole idea of intermolecular forces, we can describe things as being volatile or non-volatile. A volatile liquid or volatile liquid is going to be one that easily vaporizes. A volatile liquid, therefore, is going to be something that has weak intermolecular forces. An example is propane. Propane has weak intermolecular forces. It is considered to be a very volatile liquid, hence the reason it is used to heat homes. Octane. While octane has a stronger intermolecular force than does propane, it still has weak intermolecular forces because all octane has is the London dispersion forces. Since all it has is London dispersion forces, that means that it is going to have a weak intermolecular force, therefore it's going to typically be a volatile liquid. That's the reason we use octane as fuel for vehicles. Now, your non-volatile liquids are going to be liquids that do not easily vaporize, meaning they have strong intermolecular forces. Water is an example of a non-volatile liquid. It does not easily vaporize. Relatively speaking, because it has much stronger intermolecular forces. If you were to heat metals so that they form liquids, such as iron, forming liquid iron, again, it is going to be a non-volatile liquid because iron is going to have an extremely strong intermolecular force, even in its liquid phase. So this is just some terminology that you're going to encounter as you go through the process. And what does it, and this basically explains what it means. So looking at things, water has a normal boiling point of 100 degrees Celsius. Again, normal means that it is occurring at 1 atmosphere of pressure. When we say something is a normal melting point or normal boiling point, we're describing the temperature at which that occurs at 1 atmosphere. Rubbing alcohol, which also is has hydrogen bonding forces, has a normal boiling point of 82.3 degrees Celsius. Now, when you decrease the strength of the intermolecular force, you significantly decrease the temperature at which the normal boiling point occurs. For example, acetone and diethyl ether. Both of these, all they have are dipole-dipole forces. And you will notice that their boiling points are significantly less than that of water and rubbing alcohol, which have hydrogen bonding forces. We're also going to talk about enthalpy of vaporization in greater detail. The enthalpy of vaporization, remember, enthalpy is heat. So we're talking about the heat of vaporization, the heat needed to vaporize. You will notice again that the compounds that have a hydrogen bonding have an extremely high enthalpy of vaporization compared to compounds that have simply dipole-dipole forces, which are much weaker. They have a lower enthalpy of vaporization. The enthalpy of vaporization, by the way, is going to be much larger, as we will see, than the enthalpy of fusion. The enthalpy of fusion describing the energy needed to convert a solid into a liquid. So again, when we are talking about the vaporization, the vapor pressure of a compound is associated with its dynamic equilibrium. Again, when you have a liquid, some of these molecules are going to have enough energy in order to escape and go into the gas phase. Originally, if all you have is liquid, then you're going to have nothing but molecules escaping going into the gas phase. Now, once they're in the gas phase, they're going to move around rapidly and they're going to encounter the walls of their container. They're going to encounter each other. When they encounter the walls of the container or they encounter each other, they lose some of their energy. Once they lose enough energy, some of those molecules will begin to go back into the liquid phase. What happens when you're measuring the vapor pressure is you're measuring the dynamic equilibrium that occurs, which means that the rate of evaporation equals the rate of condensation. Meaning the amount of gas and the amount of liquid does not change. Now, vaporization is temperature dependent. If you have a cold liquid, you're going to have a much lower amount of vaporization. You're going to have fewer molecules that gain enough energy to go into that gas phase. So you're going to have a lower vapor pressure. As you increase the temperature, though, you're going to increase the amount of molecules that have sufficient energy to break that liquid phase and go into the gas phase. So you're going to have more gas molecules. At higher temperatures, since you have more gas molecules, you're going to have a higher vapor pressure. So vapor pressure is temperature dependent. The higher the temperature, the higher the vapor pressure. Questions so far? As I've said multiple times, I love questions. Yes. You are, and I'm about to get to that. Some other key points, and I've actually already made these key points. Boiling point is the temperature at which the liquid's vapor pressure equals the external pressure. The boiling point is the point at where the liquid's vapor pressure equals the external vapor pressure. So in other words, outside pressure and inside pressure are the same. Now, when we add the word normal in front of the word boiling point, then we're being very specific as to what that outside pressure is. At anything that is described as normal, it means that the outside pressure is 1 atmosphere. So if we just use the blanket term boiling point, it's dependent upon the pressure outside. But when you add the word normal in front of the boiling point, you're specifying exactly what pressure you're dealing with. That's the difference between the term boiling point and normal boiling point. A lot of our questions are going to be related to normal boiling point. if vapor pressure is temperature dependent. And this graph actually should look not perfectly familiar, but it should be somewhat familiar. And the reason it should be somewhat familiar is on Monday in the lab, we did a graph, except we focused on dichloromethane. What you will notice is at 0 degrees Celsius, our compounds have a very specific vapor pressure. Water and ethanol or ethyl alcohol, which both have hydrogen bonding, have a much lower vapor pressure at 0 degrees Celsius. But diethyl ether having dipole-dipole forces as its maximum force, has a much higher vapor pressure at 0 degrees Celsius. So again, the vapor pressure at any given temperature is related to the intermolecular force. The stronger the intermolecular force, the lower the vapor pressure at that temperature. Now, as you increase the temperature, as we showed a couple of slides ago, you're going to increase the vapor pressure. That is because as you increase the temperature, you're giving the liquid molecules sufficient energy in order to break that surface tension. You're giving the molecules sufficient energy so that they can go into the gas phase. And therefore, we're increasing the vapor pressure because we have more gas molecules in the gas phase. At 760 torr, which is 1 atmosphere, this would be the normal boiling point, and therefore the vapor pressure associated with that normal boiling point. For ethanol, that normal boiling point is 78.3 degrees Celsius compared to water. That is because water has greater hydrogen bonding than does ethyl alcohol or ethanol. We're going to see this graph again here in a moment. So vapor pressure, you will notice that the temperature and the vapor pressure are directly related, but they are not a linear relationship. They are an exponential relationship. You will notice temperature and vapor pressure are directly related. You increase the temperature, you increase the vapor pressure. But it is not a linear relationship. It is an exponential relationship. So let's talk about the equation that describes this exponential relationship. We're going to talk about the equation that describes that exponential relationship. The P of vaporization is equal to beta times the exponential value of a negative enthalpy of vaporization over RT. Or in other words, P of vaporization is equal to beta E to the power, where this is the power. Now, as I described in the laboratory, we do not like exponential equations most of the time. We want linear equations. So we perform a mathematical process in order to convert an exponential equation into a linear equation. And in this particular case, that mathematical process is to multiply the entire equation through by the natural log. So we have the natural log of the pressure at vaporization is equal to the natural log of the right-hand side. Now, if we take the natural log and multiply it by the pieces within the bracket, you get the natural log of the vaporization of pressure, or the pressure at vaporization is equal to the natural log of beta plus the natural log of the exponential of the natural log of E raised to the negative delta H of vaporization over RT. Log, the natural log cancels out the exponential. And so the equation becomes the natural log of the P of vaporization is equal to the natural log of B plus negative delta H of vaporization over RT. The enthalpy of vaporization for a particular substance is a constant for that substance at a given temperature. R is also a constant. So we can rearrange that equation further, and the natural log of vaporization is equal to negative enthalpy of vaporization over R times 1 over T plus the natural log of beta. This, folks, has the formula Y equals mx plus b, which is a linear equation called the Clausius-Clapeyron equation. The Clausius-Clapeyron equation is fantastic for determining the enthalpy of the reaction. As long as we know the pressure and the temperature, we can determine the enthalpy of the reaction. Or the enthalpy of vaporization, I should say. Again, that enthalpy of vaporization is going to be the energy, that the heat required to take a liquid and convert it into a vapor. So basically, the one last thing I will say is the R here equals 8.314 joules per mole Kelvin. The R is a constant. The R is a dictator of units, meaning that our enthalpy is going to have to be in joules in order to perform this calculation, meaning our temperature has to be in Kelvin in order to perform this calculation. Now, you'll notice that there's no pressure unit here. That means that the pressure unit, it can be in torr, it can be in atmospheres, it can be in whatever. But the right-hand side of this equation is specified. Yes.
What is the beta stand for?
Beta is, this is going to wind up being a constant. It's going to be the y-intercept. It's not, it's just a constant for the equation based off of the graph. It's just a numerical value. So let's work with the Clausius-Clapeyron equation. In lab, graph 4, we created a line by plotting 1 over t on the x-axis and the natural log of p on the y-axis. When we created that linear line, our slope of the line was a negative 3773 Kelvin. What is the enthalpy of vaporization of dichloromethane? Okay, so slope, that's our M. Our M value is equal to a negative delta H of vaporization over R, where R was equal to 8.314 joules per mole Kelvin. So if our slope is a negative 3773 Kelvin, that's going to be equal to our negative delta H of vaporization over 8.314 joules per mole Kelvin. Now, the negatives, if you multiply everything through by a -1, you get 3773 Kelvin is equal to our delta H of vaporization over 8.314 joules per mole Kelvin. Multiplying both sides through by 8.314, you get a value of 31,368.7 joules per mole. Now, as we learned in College Chemistry 1, enthalpy is typically reported in kilojoules per mole. So we would need to convert that out of joules into kilojoules by dividing by 1,000. So our answer comes out to be 31.4 kilojoules per mole. Yes.
Like original equation, so like negative H evaporation over R is the slope. So why, when negative 3,000, like it says the slope, why is it in the H evaporation instead of like it's in the Y position, but why is it in the slope position?
Hey, I think I understand. Let me go back to the equation. So when you rearrange the equation, you can rearrange it so that this times 1 over t, your 1 over t is your x, and the slope is negative delta H of vaporization over R. I don't think I'm understanding your question.
Like I'm confused why that wasn't the delta H that. Like I'm confused, like why weren't we solving for Y? We were solving for the slope.
Oh, why were we solving for y instead of this? So the question is, why were we not solving for y instead of the slope? Why were we not solving for the natural log of vapor pressure instead of the enthalpy of vaporization? The answer to that comes into play with what we actually graphed. When we were graphing, we graphed 1 over t on the x-axis, so we had all of our temperatures, and we graphed the natural log of pressure on our y-axis. So we had all of our natural logs of pressure. that means that we had y and x of our equation. And when we told it to give us an equation on our graph, it gave us y equals -3773 x plus b. So in other words, it was giving us that -3773 was the slope, and therefore it is specifically equal to this particular quantity because of the way the equation comes out. Did that answer your question? Yeah. Okay. So again, we have an enthalpy of vaporization of 31.4 kilojoules per mole. That was for our dichloromethane example that we used in lab. Now, the Clausius-Clapeyron equation can be extended to a two-point form. And in this two-point form, we can calculate one of our pressures if we have an unknown pressure. Or we can calculate one of our temperatures if we have an unknown temperature. In the two-point form, basically what it is it's a ratio of equation of the first equation to the second equation. And when you do that ratio, you wind up with the natural log of P1 over P2 is equal to the negative delta H of vaporization over R times 1 over T2 minus 1 over T1. Here, the P stand for pressure. Again, it does not matter what unit your pressure is in as long as the two pressures have the same unit. However, because of that R value, again, R is equal to 8.314 joules per mole Kelvin. Your temperature has to be in Kelvin. By the way, you don't have to memorize these equations or constants. The equations and constants will be given to you on a formula constant sheet at the back of each exam. So let's look at an example. Methanol has a normal boiling point of 64.6 degrees Celsius and a heat of vaporization of 35.2 kilojoules per mole. What is the vapor pressure of methanol at 12 degrees Celsius? That's what I get for typing so early in the morning. Okay, let's break this down. Normal boiling point means what is the pressure? The pressure is 1 atmosphere. That will be our first pressure. And our first temperature is 64.6 degrees Celsius. The heat of vaporization, so delta H of vaporization is 35.2 kilojoules per mole. We have been asked to determine the vapor pressure, so P2 of methanol at a T2 of 12.0 degrees Celsius. Looking at the equation that we are going to use, it's the natural log of P2 over P1 is equal to the negative delta H of vaporization over R times 1 over T2 minus T1. So, in order to have all of the information, we need our R value. Our R is 8.314 joules per mole Kelvin. Again, it is a dictator. It's telling us that our temperatures better be in Kelvin. So 64.6 plus 273.15 means that our temp T1 is equal to 337.75. Our T2 is equal to 285.15. It's also telling us that our delta H of vaporization has to be in joules. So that means it's 35,200 joules per mole. Now that we have everything in the correct units, we can do this math. The natural log of P2 over P1 is equal, or excuse me, over 1 atmosphere. Is equal to a negative 35,200 joules per mole divided by 8.314 joules per mole Kelvin times 1 over T2, 285.15 Kelvin, minus 1 over T1, which is 337.75 Kelvin. The right-hand side simplifies. No. Insert. Well, we'll just do this. The right-hand side, so we have the natural log of P2 over 1 atmosphere is equal to negative 2.31. Yes. It should have been P2 over P1. Now, looking at this, to get rid of the natural log, we're going to take e to the natural log of P2 over P1. which is 1 atmosphere, is equal to E to the negative 2.31. Taking the E of natural log cancels that out, and you get P2 over 1 atmosphere is equal to E to the negative 2.31. That gives us a value. No. P2 over 1 atmosphere is equal to 0.0993. Multiplying by the 1 atmosphere, that means P2 is equal to 0.0993 atmospheres. Questions? Folks, the secret to the Clausius-Clapeyron equation, whether it's the 1-point form or the 2-point form, is number 1, recognizing that the 1-point form fits y equals mx plus b. The 1-point form is excellent for determining the enthalpy of vaporization. Not to say you can't determine the enthalpy of vaporization off the 2-point form, but the 1-point form is excellent if you're going to graph some data. It is excellent for providing the enthalpy of vaporization. Another secret to this is understanding that R is a dictator of units. It's telling you what the enthalpy of vaporization unit must be. It's telling you what the temperature unit must be. And the third secret to this is it has been really to understand that exponential and natural log are inverses of each other. That is how you cancel them out. Questions about the Clausius-Clapeyron equation? By the way, if you are using your textbook, the 1-point form of the Clausius-Clapeyron can be found on page 505. And the 2-point form of the Clausius-Clapeyron is found on page 507. So if you are using your textbooks, that is where those two equations are. That is also where some of these sample questions come from. Okay. So I started college chemistry 2 with a picture of the 3 states of matter. a solid that is melting to form a liquid. A liquid that is evaporating to form a gas. In all of those cases, I said we're going to add positive energy, positive enthalpy must occur. Now we can go in the opposite direction. We can take a gas and we can condense the gas to form a liquid. And we can take the liquid and we can fuse the liquid to form a solid. That process would have negative enthalpy because it gives off energy in order to go from a gas to a liquid and a liquid to a solid. I then also talked about the fact that we could go directly from the solid to the gas through a process called sublimation. And we can go from the gas back to the solid through a process called deposition. These are our processes. What we're going to discuss now is specifically the heating portion. And we're going to discuss the energy, specifically the heat needed to go from a solid all the way to a gas. This is section 11.7 in your textbook. When we develop a heating curve, it has 5 segments. The first segment is dealing with a solid. It is the segment from the melting or from the freezing point down. So basically, this first segment is nothing but a solid. If we are talking about water, we're talking about everything from 0 and down in temperature, in degrees Celsius. A solid is going to be a very organized substance. Now, the second segment represents the enthalpy of fusion. The enthalpy of fusion is going to be the point where some of that solid that's all nice and tidy is going to be occurring simultaneously with liquid molecules that are less tidy. We will have to add energy in the form of heat until we can break many of those intermolecular forces in the solid in order to get them into liquid form. The third segment represents a pure liquid. The fourth segment, and we'll have a liquid from the melting point to the boiling point of the substance. In the case of water, that means from 0 degrees Celsius to 100 degrees Celsius, we will have a pure liquid. The fourth segment represents the enthalpy of vaporization. It is that energy needed to convert the liquid to a vapor. Now, when you're in this segment, the two states of matter are in concert with one another. You have the liquid and you have the vapor. It is only until you can break all of those intermolecular forces that we encounter the fifth segment, which is that of a gas. And a gas will have a temperature anything above a boiling point. So heating curves have 5 segments. 3 are the states of matter that we have been talking about: solid, liquid, and gas. The other 2 describe the heat needed to overcome intermolecular forces. In the case of the enthalpy of fusion, it is to overcome part of the intermolecular forces. In the case of the enthalpy of vaporization, it is the energy needed to overcome all of the intermolecular forces. You will notice that this line for the enthalpy of fusion is much shorter than the line for the enthalpy of vaporization. Again, it's because of the intermolecular forces. We're only overcoming some of the intermolecular forces here. So it is shorter. Here we have to overcome all of the intermolecular forces. So it is much bigger. The enthalpy of fusion is much smaller than the enthalpy of vaporization because of intermolecular forces. It does not matter what substance we're dealing with. The enthalpy of fusion will be much shorter than the enthalpy of vaporization. Now, let's talk about the heat and how we calculate the heat for each of these sections. For A, C, and E, you already have the main tool that you need. For A, C, and E, because there is a change in temperature, you're going to use your equation Q is equal to MCAT that you learned in College Chemistry 1. Now, in College Chemistry 1, you mainly focused on liquid water, liquid substances. But when we're dealing with this heating and cooling curve, you're going to have to pay attention to the state of matter because the specific heat varies based off of the state of matter. For A, you will use the specific heat of a solid. For C, you will use the specific heat of the liquid. And for E, you will use the specific heat of the gas form of that material. So again, you already have the tool needed to calculate the heat associated with A, C, and E. It is B and D that is new, that is completely new to us. For B and D, Q is going to equal N times the enthalpy. Here, N represents moles, whereas up here, M represented mass in grams. Now, in B, we're going to use the delta H of fusion for our enthalpy, whereas in D, we're going to use the delta H of vaporization for the enthalpy. Again, notice even though it's not as obvious on this particular graph, notice that B is shorter than is D. That is because the enthalpy of fusion is always going to be less than the enthalpy of vaporization because of what it stands for with respect to intermolecular forces. So let's look at an example. Calculate the heat needed to raise the temperature of 18 grams of water from a negative 25 degrees Celsius to 125 degrees Celsius. Okay, first of all, let's develop our heating curve. It's always going to have those 5 segments. Now, because this is water, we know that the melting point of water is 0 degrees Celsius, and we know that the boiling point of water is 100 degrees Celsius. Now, we want to go from a negative 25 degrees Celsius, so down here, to a positive 125 degrees Celsius, so way up here. So we're going to need all 5 segments. We're going to have to perform 5 calculations and then add the results of those 5 calculations together in order to get the answer. Again, we have to have all 5 segments. So that means we're going to have to perform 5 calculations and then add up the answers to those calculations to get the ultimate result. Okay. So let's look at the first segment. Segment number 1. We had ice. Ice was going from an initial temperature of a negative 25 degrees Celsius to a final temperature of 0 degrees Celsius. Because there is a temperature change, we're going to be using Q equals MCAT, where the C is going to be that of a solid. So our Q is going to equal 18 grams times the specific heat of solid, which was 2.09 joules per gram degree Celsius, times T final of 0 degrees Celsius minus T initial, which was a negative 25 degrees Celsius. So our Q for this process is 940.5 joules. That is segment 1. Segment number 2 is the process where ice is converted into a liquid. So we're going to need to use the delta H of fusion, which was given to you as 6.02 kilojoules per mole. The equation for this process is Q is equal to the moles times the delta H. Well, the first thing we need to do is convert that grams into moles. So 18 grams of water converted into moles of water using the molar mass of water means that we have 1 mole of water. So our Q here is going to be equal to 1 mole of water times the delta H of fusion, which is 6.02 kilojoules per mole. So that means that we are dealing with a Q of 6.02 kilojoules. Segment 3. We are dealing with liquid water. Our initial temperature was 0 degrees Celsius, and our final temperature was 100 degrees Celsius. This time we're going to be using Q equals MCAT, but our C is going to be for that of a liquid. Q, therefore, is going to equal 18 grams times the specific heat of 4.18 joules per gram degrees Celsius times T final of 100 degrees Celsius minus T initial, which was 0 degrees Celsius. So we get a Q of 7,524 joules. Now we need to do segment 4. Segment 4 was the point at which a liquid became a gas. Therefore, we are going to be using the delta H of vaporization, which was 40.7 kilojoules per mole. Our equation for this is Q is equal to the moles times the delta H. So it is equal to 1 mole times 40.7 kilojoules per mole. Or in other words, it's 40.7 kilojoules. We have to do segment 5 because basically, folks, you don't always have to do all 5 segments. It depends upon where you were going from and where you're going to. In this particular case, I had to go from a solid all the way up to a gas. So I had to do all 5 segments. But that's why I drew the heating and cooling curve first, is so that I could figure out how many segments I had to do. And in this particular case, I had to do all 5. So in the last one, I had a gas. My initial temperature is 100 degrees Celsius, and my final temperature was 125 degrees Celsius. I am using Q is equal to MCAT, but specifically I'm using the specific heat associated with a gas. So Q is equal to the 18 grams times the specific heat of the gas, which was 2.01 joules per gram degree Celsius, times the final minus the initial, 125 degrees Celsius minus 100 degrees Celsius, which means that gives me a Q of 904.5 joules. Now, the question was how much heat must be added in order to go from negative 25 all the way to a plus 25. One of the things that you may note that you should have noted along the way is that our enthalpies were in kilojoules and our Q equals MCAT were in joules. So you're going to have to change one of them. You either have to change the kilojoules to joules or the joules to kilojoules. I'm going to change the joules into kilojoules. So our total heat is going to equal the Q for step 1 plus the Q for step 2 plus the Q for step 3 plus the Q for step 4 plus the Q for step 5, because we had to do all 5. Which means it was 0.941 kilojoules plus 6.02 kilojoules plus 7.52 kilojoules plus 40.7 kilojoules plus 0.905 kilojoules. When you add it all together, you get 56.1 kilojoules is how much it's going to take in order to go from a solid at negative 25 degrees Celsius to a gas at 125 degrees Celsius. Okay, on Tuesday, I'm going to pick up with one more of these, and then we're going to do phase diagrams and hopefully get into chapter 13. I will see you on Tuesday.